Hi there, welcome to lecture 6 of Fox. Today's topic is strong induction. And if you remember, we just talked about induction, and induction is so important that Orange Malik gave the lecture. Well, induction is so important that it's even worth spending a second lecture on induction. Okay. Now let me remind you what we did last time. So last time we talked about induction. Okay, how do you prove for all? And we used the induction machinery, to prove that 4 to the n minus 1 is divisible by 3 for all n greater than or equal to 1. Something that might not have been obvious, but then we proved it with induction. Okay. And then we also proved that the sum of the first n integers is 1/2 n times n plus 1. It's a very famous sum. It's worth remembering that 1 plus 2 plus 3 up to n is equal to 1/2 n plus 1. It's quite amazing that we can get a closed formula for such a sum. We can also get a closed formula for the sum of the first n squares. And, the sum of the first n squares is 1/6 n plus 1, 2n plus 1. Okay. And if you did what I asked you to do last time, and sort of read up in the book this method of differences, that's a systematic way of trying to get formulas that you might be able to prove with induction. Because one of the problems with induction is that it doesn't derive the formula for you to prove. It's a machinery for proving something once you have a guess, once you have a suspicion what the right result is. Okay. And lastly, last time I showed you that, pretty much anything you can prove with induction, you can prove with the well-ordering principle and contradiction. Okay. The so-called method of the smallest counterexample. Okay, the smallest counterexample approach. Okay. And so today, what's the plan? Since we already covered induction, it's just induction by osmosis. Induction. So we're going to start with some sort of slightly harder problem that uses induction to prove a fairly, esoteric-looking, tough inequality. Okay. And then I'm going to show you something peculiar about induction. And it's peculiar in general that, sometimes we try to prove something, we fail. And with induction, you might fail to prove something that's easy, but you might be able to succeed to prove something that's harder. And that's a very peculiar situation that occurs with induction. It's sometimes easier to prove harder things. Okay. So we'll show you examples of how this arises and why this arises, and then we'll consider many flavors of induction, leaping induction, and the ultimate sort of induction, strong induction. But I want to emphasize that all these other flavors of induction are no more powerful than the original induction that we discussed last lecture. In fact, they're all just derivatives of the original induction. So it's just that, just like, there's one way to prove an implication. Look at the truth table and argue that the true-false row doesn't occur. There's one induction, but there are many flavors, and sometimes if you use one of the flavors, it's a little easier to make a proof than if you use another flavor. But you can always prove anything with induction using the type of induction that we talked about last lecture. That type of induction is usually called ordinary induction. Today we're going to talk about strong induction. Oh wow, okay, what an exciting lecture we have in store for you. Okay, so let's get loads of practice with induction. We're going to start with a very daunting looking formula, inequality actually. So 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus and so on up to 1 over the square root of n, okay, is at most twice the square root of n. Okay. So you can think of this as an inequality involving n. So as with any induction, this is what's going to define our predicate, our P of n. So our P of n is the claim or the predicate that this inequality holds. So now we want to prove this by induction. Okay. So proof by induction. First step in any induction, base case. Okay, so the base case. Okay, and we want to make this claim for all n greater or equal to 1. So the base case is n equals 1. Okay, so P of 1. What does that claim? What it claims is that, 1 over square root of 1, so n equals 1. So you end the sum here. 1 over the square root of 1 is less equal to twice the square root of 1. So 1 over the square root of 1 is less equal to twice the square root of 1. And that means that 1 less equal to 2, which is clearly true. So clearly true. Okay, so we've established the base case, P of 1. Remember, just I'll put up here a sort of a visual of what induction is doing. So induction establishes the infinite chain P of 1 implies P of 2, implies P of 3, implies and so on. An infinite chain, and then, so we need to establish the infinite chain, and we also need to prove the leftmost claim. So we need to prove P of 1. Okay, and then this P of 1 together with the infinite chain sets up an infinite cascade of inferences that allows us to conclude that P of n is true for all n. Okay, so that's the basics of induction. Okay, and here what we're doing is we're establishing the base case. We're establishing the leftmost claim in this infinite chain. Okay, and the next step in an induction proof is to actually prove that infinite claim. So that's called the induction step. And in this case, the induction step is to show that P of n implies P of n plus 1. Okay, so we get to assume, basically we're proving an implication, so we get to assume P of n is true. So assume P of n, which is the claim 1 over square root of 1 plus 1 over the square root of 2 plus all the way to plus 1 over the square root of n less equal to twice the square root of n. We get to assume that. And now we have to prove P of n plus 1. We only get to assume this in the induction step. So prove P of n plus 1, which is the claim that 1 over the square root of 1 plus 1 over the square root of 2 plus all the way to plus 1 over the square root of n plus 1 over the square root of n plus 1 less equal to twice the square root of n plus 1. Okay. This is the fundamental induction mechanics. Okay. And it's very good. You might not see exactly how to prove P of n plus 1 starting from P of n, but it's very important that you actually just know the mechanics. You should be able to set up the induction proof. Okay, now the creativity in an induction proof is to somehow figure out how to relate the claim that you're trying to prove to the claim that you can assume that you can assume to be true. And in this case, it's reasonably straightforward because we observe that this is a sum that includes this sum plus an additional term. So we know that 1 over square root of 1 plus 1 over the square root of 2 plus 1 over the square root of n is less equal to 2 square root of n. That we know. Okay? This is what's called the induction hypothesis. Okay? And if we add 1 over the square root of n to both sides, then we get 1 over the square root of n plus, all the way to plus 1 over the square root of n plus 1 over the square root of n plus 1 is less equal to 2 square root of n plus 1 over the square root of n plus 1, because I've added 1 over the square root of n plus 1 to both sides. Okay, and now this is where this induction proof gets hard. It's not the case that all induction proofs are just trivial and it's easy to prove this implication. Now we are wondering what the heck to do now. Okay, because this doesn't look anything like that. Okay, and indeed, there is no way to simplify this to get that. Even though we have the left-hand side, it's not easy to simplify this to get that. But we don't need this to equal that. Okay, we just need this to be less than or equal to that. So, question: is it true that the 2 square root of n plus 1 over the square root of n plus 1, 2 square root of n plus 1 over the square root of n plus 1 is less equal to 2 square root of n plus 1? Question mark. Turns out, yes. Okay. And let me prove it to you quickly. So, and I'm going to call it a lemma. So this introduces you to the concept of a lemma. It's still a claim. It's just that, it's not a claim that is important in and of itself. It just tells the reader, I'm about to prove a lemma. I'm about to prove a claim that I don't really care about so much. It's just that I need the claim. I need this lemma in order to prove something else. So lemma. Okay. For n greater equal to 1, it is the case that twice the square root of n plus 1 over the square root of n plus 1 less equal to twice the square root of n plus 1. Just claiming that as a side result. Okay. Now, proof by contradiction. So this is nice because it also gives us a little bit of practice with some other proof techniques, in this case, contradiction. So how does a proof by contradiction start? It starts by assuming that whatever you're trying to claim is false. So assume twice the square root of n plus 1 over the square root of n plus 1 is less equal to is greater than twice the square root of n plus 1. Now, Usually when you have, equations like this, it helps to simplify. And we can simplify by multiplying both sides by the square root of n plus 1. In this case, this becomes 1. The square root of n plus 1 times square root of n plus 1 is just n plus 1. And this becomes twice the square root of n times n plus 1. So, if we multiply by square root of n plus 1, we get twice the square root of n plus 1 is greater than twice n plus 1. Okay? If we subtract 1 from both sides, we have that twice the square root of n plus 1 is greater than 2n plus 2 minus 1. So 2n plus 1. Okay? And now squaring both sides again, we have that 4n plus 1 is greater than the square of this guy, which is 4n squared plus 4n plus 1. This is 4n squared plus 4n. 4n is greater than 4n squared plus 4n plus 1, or, if I cancel out the terms involving n, or 0 greater than 1. That is fishy. Okay, and technically we call it a contradiction, and that's the end of the proof. But the moment I come to something fishy, it means my starting assumption was wrong, and that means that my lemma, which is just a way of saying helper claim or helper theorem, just like we have helper functions when you program. This is a helper result. Okay, our lemma is proved. But by this lemma, it means that this guy here is less equal to, so this plus this, the lemma claims that this plus this is less equal to twice the square root of n plus 1. So, but look, this guy less equal to this guy, which is exactly what I wanted to prove. Okay. I wanted to prove that this ugly-looking complex sum is less equal to this. And that establishes the induction step, because this is what I needed to prove. Therefore, Pn plus 1 is true. Okay, and now we have established the induction step. We've established the base case. So by induction, okay, P of n is true for all n greater equal to 1. Okay? Hard induction proof. No problem. Okay. You can do hard proofs too. There's nothing wrong with that. Okay. So let me erase.